Welcome and thank you everybody for joining us for another episode of the Jane Irrigation Training Series. I'm Richard Restuccia, Vice President of Water Management Solutions for Jane Irrigation. And today I'm really excited to be talking about soil, plant, and water relationships. And the reason I am is because oftentimes, in our training series and our episodes, we talk about specifics of just one or the other, right? We might talk about water or irrigation. We might talk about fertilizer for soil, but oftentimes we neglect that there is a symbiotic relationship between the three, and really viewing it from that perspective is the way that you're going to be the most successful, whether it's in your fields or in your landscape or in your garden. And the one thing that we really have going for us today is we've got Dr. Gaudi today taking us through this journey. He works at Cal Poly San Luis Obispo. He's the product manager for the ITRC. He's a certified irrigation designer. He's a irrigation specialist, and he's also a certified crop advisor. So he comes with a ton of experience and certifications, but I'll tell you a couple of things that I really admire about Dr. Gaudi. We've had him on here before, and based on the hundreds of people that signed up for this, he's very popular. He's a good teacher because of that. And one thing that I learned early on is that, and we've all had these teachers in our lives that take somewhat common subjects and make them very interesting. And Dr. Gaudi possesses that ability to do that. And I think that's why he's so successful. So anyway, Dr. Gaudi, thank you for joining us, and welcome.
Yeah, thank you. Thanks for those kind words. I don't know how much of it's true, but I appreciate it.
It's all true, let me tell you. So one thing, I think it might be helpful for everybody to hear to start off here is what is the ITRC? What exactly is that? What do you guys do?
Yeah. So the Irrigation Training and Research Center is a center housed within the Bioresource and Ag Engineering Department here at Cal Poly. And our mission is basically to teach irrigation to our undergraduates, and we also have some grad students in our program as well. So our mission is to basically educate future generations of farmers and water managers and so forth. So Dr. Charles Burt, he started the center in 1989. And our primary goal then was education, but we also do research and we do projects as well. So some of you maybe are with irrigation districts. We've worked with, hundreds of irrigation districts. And so we're really tied to the Bioresource and Ag Engineering Department here. And our department is, with COVID and so forth, it's been challenging to recruit students. Because I think a lot of students are like, well, I've been sitting at home on my computer for, the last 2 years, basically doing school. And I don't want to continue sitting in my living room doing school, just saying I'm going to Cal Poly now. They actually want to come to Cal Poly. And so I think for that reason, we've struggled to get some attendance in some of our major courses. So we have 2 programs in our department. One is Bioresource and Ag Engineering, and then the other one is called Agricultural Systems Management. One is engineering related, the other is a technical program. And those 2 programs compared to other programs here at Cal Poly are, I'm going to say, without sounding bad, I want to say they're a little easier to get into. Like, for example, if you wanted to compare mechanical engineering to our ag engineering program, ag engineering is a lot more, a lot less resistance, let's say, to get into ag engineering, just because a lot of students don't understand what ag engineering is. So, so I'd encourage you, if you have any students that are, high school age, sophomores, juniors, to maybe consider looking at the Cal Poly as a potential option, and also, maybe even working in the industry, maybe working for ITRC as a student employee. We hire dozens of them typically during normal years, for this. So consider looking at the ITRC website and or the BRAE website. If you just search ITRC Cal Poly or BRAE, BRAE, Cal Poly, you'll find them. So
great suggestion. Both the school and the department have some of the highest reputations we see in higher education. So it's a great heads up that this might be a special time to get involved. So thank you.
absolutely. Yeah, thank you. All right, so I'll go ahead and get started here with the presentation. If you have any questions along the way, go ahead and type them into that chat function down there. Between Richard and I, we'll pause for a moment and get them answered. I'd rather probably answer your questions while we're going rather than waiting to the end, just so that way, you're not trying to figure out one thing and then you miss 5 things because you didn't have that one answer. So feel free to type away in that chat and I'll answer. I'm going to be doing this a little bit differently than probably most presentations, in that I don't have a PowerPoint. We're going to do some whiteboard work here. We're going to do some like traditional schooling, so to speak. So I want to just pull up a whiteboard for you here, and then we'll get started on some of the basics of soil plant water relationships.
Okay. It's interesting that you say traditional education, right, on a whiteboard that's on a computer.
Yeah, that's right. Yeah, that's true. Digital whiteboard. All right, so you can see my screen now with the whiteboard, correct?
It looks great, yeah.
All right, so again, there's the Cal Poly and the ITRC logos there, and so there's the exact wording for the Bioresource and Engineering Department if you want to take a look at that. So today we'll cover soil plant water relationships, and I'm going to talk a little bit about soil moisture sensors, because some of you are probably using soil moisture sensors as well. But I think in order to understand how the soil moisture sensors are working, you really have to kind of understand what the soil plant water relationships are. Okay, and so I want to start with 2 ideas here, and the first is soil structure, okay, versus soil texture. Right, so these are 2 things that sometimes get mixed up here: the soil structure versus the soil texture. Right, and the soil texture is probably the one you're very familiar with, and that's the one that's basically you have your sand, your silt, and your clay, right? Those are kind of the 3 main textures, and then of course you mix them up, and then it's like how many combinations that are in a bag of Skittles, right? I mean, you get all kinds of different combinations of soil texture. Soil structure, on the other hand, is how the soil particles are oriented, right? And so I've got actually down here, I've got a couple pictures here to describe soil texture and soil structure. Okay, so the triangle you probably have all seen. This is just your standard texture analysis. Now, when you're in the field, right, how do you determine what the texture is? Now, some of you have probably done enough work that you can, you can just say, by looking at it, well, that's like a loam soil, right? And so what is a loam? That's kind of the first thing we need to talk about, because we said they're sand, silt, and clay, but we haven't really described what a loam is. And so one of the misconceptions of a loam soil is, at least with my students, who, by the way, probably don't have quite as much experience as you do working with this, but they always assume that a loam is basically a third, meaning it's 1/3 sand, 1/3 silt, 1/3 clay. But in reality, it's not. If you look here at how to read this, right, you'll notice these numbers are sloped in this direction. So we're going to read it in this direction here. So for example, on the sand, a loam actually is 40% sand. Then you look at the silt, right? And so we read this one down to here, right, like this. So it's 40% silt. And then you read the clay coming over, and it's actually 20% clay. So a loam soil is actually right around 40%, 20% in terms of what the makeup is of a loam soil. And so just looking at this here too, one of the things I want to point out is if you look across here, right, if I was to kind of highlight it like this, you see that a large chunk of this triangle here, that part that I just highlighted there, is all considered to be some kind of loam, right? Clay loam, silty loam, sandy loam, depending on which direction you are. But loam ends up taking up a kind of a big chunk of the amount of, or the types of soils that we have out there. And of course, this is showing just the basic soils. I mean, you can get into really fine detail of the types of soils that you have. One of the things I might show you real quickly here, it just kind of hit me. I didn't quite really prepare for this. That's our website actually here. But if you go to there's this deal called Web Soil Survey. And the Web Soil Survey is it's an NRCS website. And on this website here, if you don't know what your soil type is, right, and you want to have a ballpark idea of what it is, you can go to the Web Soil Survey, and then you can pull in basically a map, kind of like a Google map of it, and you can zoom into your particular location here, right? And so I'm just going to zoom into some spot here in California. Let's go over here, maybe somewhere where we have some fields, right? And we can just zoom in to right in here somewhere. And then you could basically, you could ask this thing, and I'm not going to go through the whole process here because it does take a few minutes to generate it, but you can draw a polygon around your particular field, and then you can say, what is the soil type? And it will pull in your soil texture based on historical data for that particular area. So it does get you kind of close to knowing what your soil texture is. All right, so that's a good little resource that's available to you, Web Soil Survey. Okay, so going back to this, you know, the idea here is that when we're talking about soils out in our fields, most likely we're not going to be, you know, pure sand, right? If you're pure sand, you're probably on the beach, and you're probably, or maybe in a wash or something, but you're probably not going to be farming pure sand. On the other hand, you may be in an area that's predominantly clay, right? And in fact, you know when you're in a predominantly clay area because you have what are called cracking clay soils. When it dries out, they physically crack open, and you can see big, you know, 1/4 inch to 1/2 inch gaps in the soil. And so that's when you know you have lots of clay content. And then silt, you know, that's the powdery stuff that clay does too. But that's, you know, if you ever watch the Baja races, right, and they go through those silt areas, you just see the dust flying as they're going through it. So there are ways, in addition to the Web Soil Survey, you can do a by feel analysis. The NRCS also has a pamphlet on determining how much texture you have by feeling the soil. You're feeling for grittiness, you're feeling for slickness, you're trying to make ribbons to determine, you know, how much clay content is in the soil. There's actually very good YouTube videos on a lot of that you can find. And then the way that they do it in the lab is if you were to send a soil sample of soil to the lab is they basically put it in what are called sieves, and they start out, they're basically screens, you know, with certain size holes through it, and they start out very coarse, and then as you go down, they get finer and finer and finer. And then they put it on a shaker table, and they just let this thing shake, and of course you have to grind up the soils before you do it. You don't want dirt clods in there and so forth, but they shake this table, and then the soil particles will settle in different size openings. And so then the lab can basically look at that and say, okay, well, the stuff that made it down towards the bottom is more clay in nature. The stuff that made it, or that's still up in the top, is more sandy in nature. And so percentage-wise, they can figure out what soil texture you have by doing it in the lab. Now, the problem with that particular method, though, is that you send them like a couple cups of soil, right? And they do this analysis for you. And if you were to move over in your field 10 feet and send them 2 more cups of soil, you probably get a different answer. You know, maybe not dramatically different, but it's going to be slightly different. And so with that said, we're not really too concerned about how much, you know, or what exactly soil texture we have out there, because in the end, we're going to just be making good estimations of what we have anyways. Okay. So that's soil texture. Soil structure, on the other hand, again, is how it's oriented. Right. And so I've got, let me zoom into this maybe a little bit here so you can see it. We've got different orientations for the soil. And so going through the list here, granular is really the one you want. You kind of want like a bunch of pebbles or BBs out there in the field. That allows for decent drainage of water. It allows for the water to infiltrate. It also allows for roots to grow very well, give you a good structure, right? Blocky is kind of like bigger chunks. It's kind of similar to granular, but they're bigger in size. Not terrible, but probably not as good as granular. Prismatic and columnar are really kind of the same, where you have vertical orientations of your soil particles. This is challenging when you're irrigating, say with surface irrigation, because then your water will just go straight, you know, through the soil profile basically and down into the groundwater. The small difference between these two is that typically there's a salt cap on the columnar orientation. And so actually in that case, it causes some infiltration issues sometimes, depending on how much salt you have. Platy there is exactly what it sounds like. It's like a bunch of plates stacked up. And so getting roots, right? Getting roots to try to grow through this is very challenging. And also getting water to try to go through that is very challenging. And so, typically that's caused by compaction, right? From equipment or whatever. And then this is basically sand, right? I mean, you can't get a structure out of sand, even with a little bit of water, it still will fall apart. I mean, you can kind of make a ball out of it, but it's weak, and it'll fall apart. So you don't really get structure on sand. You could, though, kind of assume sand is kind of being like a microgranular structure, right? A little bit. And then massive is just these big chunks of soil that nothing can grow in, and they're really compacted. And so you end up with a bunch of blocks out there. Imagine cinder blocks or something stacked out there and you're trying to grow through that. It can happen, but it's not the best, right? And so that's in some cases, this is maybe why you're doing the deep ripping or the plowing, is to break up those massive structures or the columnar or prismatic structures, right? Ultimately, we want to get to this granular structure. And of course, there's research out there that says that no-till methods actually are better at keeping the granular structure, because the roots go out there, they kind of break up, that they make pathways in the soil. And then when the roots decay, they basically, shrivel up, and then you're left with these channels and so forth. And so it's better. So I'm not here to advocate for, no-till, because I know lots of growers like the conventional methods as well, but that is one reason why they say that no-till is a decent option.
Now,
Okay.
if I dig down in my soil, 24 or 36 inches, might I find different profiles at different levels?
Absolutely, yes. Yeah, so typically the A horizon, right, is this topsoil, and that's the soil where you're going to find most of your nutrients. See, because most of your nutrients have a positive charge, and clay particles in particular, silt and sandy soils actually don't hold nutrients. Only clay particles do. So the clay particles actually have a negative charge. And so when you apply calcium, for example, it's actually got 2+ symbols on it, right? And potassium has a plus symbol on it. Even salt, sodium, has a plus symbol on it. So all of those nutrients, they go and they find I explain it to my students as this clay soil has parking lots, parking spaces, right? That's the negative charge. And so these nutrients will go down and they'll just find a parking spot and they'll sit there until it's either maybe consumed by a plant or something else pulls it out of the parking spot, right? And so what you end up having is you have these soils that have a lot of capacity when they have lots of clay in them. And so for that reason, a lot of the nutrients are in the top, horizon there, the top 6 inches, maybe a foot, because that's where you have, that's where we typically apply the fertilizers, right? So as you go down deeper, you typically don't have as much nutrients, just for the simple fact that there's a lot of parking spaces if you have clay soils up in that top zone. And so this is sometimes why people will plow and flip it over, right? Because they're trying to maybe mix up, get rid of that B horizon, down there, or make it a little more homogeneous in say top 3 feet or so, to try to, improve infiltration and average out, your holding capacities and so forth like that. So yeah, you can definitely find horizons. If you were to ever auger in a field, right, you're going to find it's maybe clay with some root structure and so forth in there. And then it goes into, maybe a sandier soil, and then it goes back to a clay layer, depending on where you're at, right? But yes, absolutely, it can change. And the structure can change too, in different horizons. So sometimes when you have infiltration problems, right, you're irrigating and the water's just not going into the ground. It's maybe not at the surface that the problem is. You actually have compaction that's 2 feet deep, and so at that point the water's stacking up from there all the way up to the surface. Okay, all right, so let's go back up to here then. So just to kind of, I don't know where there it is. All right, so just to kind of continue on with this, so soil texture and structure, right, those are the two kind of main important pieces here. And of course, you can fix structure, right? We can do work whether it's going no-till or whether it is tilling or whatever the case is, right, to kind of fix structure. But texture, you're stuck with whatever land you're farming or you own, right? That's just the way it is. And so you could of course import it and so forth, but that's way too expensive. So if you're in these areas, you typically are going to have what you have. So I want to now actually let me show you one thing real quickly. You all know that clay holds more water than sand. Why is that, right? A clay particle, just to maybe put this into a little bit of perspective, of course, on a bigger scale here, a clay particle maybe is like a baseball in size, right? It's not physically, but I mean, if again, multiplying everything by however many times, right? It's maybe like a baseball. Okay. Actually, let's use a golf ball. Let's use a golf ball for sand. Silt is maybe more like the baseball in size. And then clay, wait, I'm all backwards here. I'm going backwards. I wrote it backwards compared to how I'm writing it. So clay is your salt, man, time out. Let's go back.
It's reversed.
I got it written reverse than how I'm talking about it. That's what's messing me up here. So my apologies. So yeah, clay is kind of like your golf ball. Silt is like your baseball. And then sand is like your basketball in size, right? And so just to kind of put it in perspective, but of course on a micro scale here. So how in the world is clay able to hold more water than sand if the sand is bigger, right? Well, in order to understand that, you have to know that the water adheres to the surface of the particle. And so you might say, well, even knowing that here, right? You have your water that's adhering to the edge of this circle. It's a sphere, so it's actually three-dimensional. And you have the water adhering to your baseball and your golf ball. Well, how are we holding more with clay? Because obviously it's a smaller, particle. Well, the answer is because we can fit a whole lot more of those particles in the same area. And so the surface area exponentially grows compared to, imagine, your cheese puff thing you get at Costco, right? With all the cheese balls in it, right? If I was to ask you, is that cheese ball deal full? You would probably say, yeah, it's full right after you buy it, right? Because it's got all the cheese balls in it. But what if I was to all of a sudden take some BBs and pour the BBs in the top? Would the BBs actually work its way through the cheese balls and potentially fill up some space, right? That's not there. And then I could ask you again, is it still full or is it full now? And you'd probably say, well, yeah, it's still full. But then I could probably take some sand and pour some sand in there and the sand's going to go in between. And then I could say, is it full? And you'd probably say, yeah, it's full. And then I could take some water and I could add some water in there, right? There's a lot of pore space in there. And when you have clay particles, a whole bunch of them, you end up with a whole lot more surface area. In fact, if I was to kind of draw this up, imagine taking this sand and cutting it in half as an example, this clay sand particle here, cutting it in half. Look at how much surface area I basically just added to that sand particle by splitting it in half. Yeah. And so the more I was to cut these, right, the more and more surface area you get for the same volume of soil. So texture is what we need to kind of understand in order to do our irrigation scheduling and so forth. So continuing on with this idea, let's assume a loam soil, right? So let's assume loam. And the reason why is because, well, like I showed you on that chart, a lot of people use loam soils. Now let's pretend, Walt Disney coined this term Imagineering, right? And so it's using your imagination and engineering kind of mixed together. So I want you to Imagineer with me for a moment here. Imagine that you were to go out to the field and you were to use your square shovel, because nobody uses a round tip shovel, right? I mean, that's nonsense. Just kidding. Nobody uses a square shovel, but we're going to use a square shovel in order to pull out a chunk of soil. We're going to pull out 1 cubic foot of soil here, right? And so we're going to pull out, a box here of soil that looks a little something like this, right? And so it's going to be 1 foot by 1 foot by 1 foot tall, right? And it's a loam soil. And so I was to ask you some questions, thinking about our cheese ball example just a moment ago. How much or what percentage of this box do you think is actually soil, right? And normally, I'm not doing a webinar. I got a live audience here, and so they can give me some answers. But if you were to think about this, right, it's not 100% soil. It's not 100%. Actually, I'm getting some chat messages. This is awesome. 60%. Very good. Oh, Sam Terpstra. He was a student of mine like a while back. Now he's changing his mind because he doesn't want to change his grade. That's right, Sam. It's 50% roughly. Yeah. So if you were to, you know, if you were to basically kind of draw a line through here, about 50% of this would be soils. Okay, I'm going to zoom into this just a little bit, make it a little easier. So what does that mean the rest of it is, right? If physically, if you were able to compress, take all those cheese balls in that thing and you were able to compact them completely, right? Getting rid of all pore space, you could probably take all those cheese balls and squish it down into half of the container. So what does that mean the other half of the container is, right? Well, it means it can be one of two things. It could either be, you could say it's all air, right? Or you could say the other half, if we were to pour water in it, could be all water. And so the question then becomes is, well, how much air and how much water, right? And so now what I'm going to do is I'm going to focus on this area between here and here, right? This is now where the soil plant water relationships come in. By the way, I do know that, you know, soils also have some organic matter in it and stuff like that. We're just ignoring that for now, because in California, if you have like 1 or 2% organic matter, we're like, yeah, we're rocking it, right? Whereas if you go to other parts of the states, you know, you might have 5 or 6% organic matter. So, but let's just pretend the organic matter and the worm is part of the 50% soils, right? So, so let's focus now on this top piece. So the way I'm going to do this here is I'm going to redraw this on a vertical scale here, right? And so this is this piece here that we're just looking at, right? So now, if, and you guys can answer this in the chat like Sam was doing, if you had 50% soils and 50% water, right? So that top half of that was completely filled with water, what would we call that condition? Anybody want to take a stab at that in the chat?
I think everybody's being shy. They don't want their name revealed.
Yeah, they don't want me picking on them.
Well, here comes some answers. All right.
All right, actually, saturation. Yeah, that's right, saturation. So we're going to get to fill capacity here in just a second. Very good. So yeah, that would be saturation. So I'm going to put that here at the top of my scale, saturation. Right, and so saturation means if we're going to, you know, kind of call it like it is, it means there's no air, right? And of course, I always have students say, well, H2O, Dr. Gaudi, there's some oxygen in there or something, right? Yeah, sure. Okay, whatever, right? Details. So, but in this particular case, to keep it simple, we're going to say there's no air in this. All right. Now, if we were to do the complete opposite of that, where we were to, you know, to have only air in the top, what would we call that condition? See if anybody wants to chime in on that one. Okay. PWP, good guess. Depletion, another good guess. Permanent wilting point, which is PWP. Air dry, we're getting closer. I can see why everybody's taking this class. Oven dry, that's it. Cassandra, that's another student of mine. All right, Cassie, kicking butt here. Oven dry is what it would be. Oops. And so that would be refill, I heard. And so we're going to call this one no water. Right? And so, yeah, so you can have any condition here, right? Of course, in this 1 cubic foot box, about 50% of it, when we're assuming a loam soil, is going to be soils, and then the other 50% can be anything between those two, from no water at all to no air at all. Right? And of course, how are we going to get to oven dry? Well, it's pretty self-explanatory. You have to physically oven dry it. So it's going back to our concept here of Imagineering. You guys have probably all done the dishes. You know, I still do the dishes in my house, right? So you have that sponge and it's just sitting on the counter, right? It's sitting on the lip of the counter and it's got the sun beating on it through the window. And it's been there for 3 days because you haven't done the dishes in a while, right? What condition are we at whenever you pick up this sponge, right? So you grab the sponge for the first time to do the dishes. It's actually not oven dry, right? Because we didn't put it in an oven. It's called air dry. And so I saw a couple guesses like this, air dry as well. Air dry is actually slightly above oven dry in that there's probably still some water molecules in that sponge. They're just tied up by the, you know, they're at such a great tension in that sponge that we can't get it out. The only way we could get it out is if we weighed it, but that's not how you get it out, but you would weigh it first, then you would bake it, and then you would pull it back out and weigh it again. And that would tell us how much water was still in that sponge. after you oven dried it. So air dry means it's very dry, but it's still got a little bit of water in it. So this is one thing I want you to note here, is that there is still water, right, from air dried all the way down to oven dry. Okay. And of course, just so we know and we're clear here, soil moisture sensors start measuring, a lot of the soil moisture sensors, not tensiometers, but the ones that measure percent moisture content, they measure from oven dry up. Okay, and this is another misconception that a lot of students have, is that they measure from permanent wilting point. And the answer, that's not true at all. Actually, the permanent wilting point just means the plant's dead. It doesn't really mean that there's no water. It's just that the plant can't get the water. It's kind of like if you were to run out of fuel in your car, there's probably still fuel in your fuel tank. You just can't get it out of the fuel tank to make the car run, right? I mean, it's, and this is why old dirt bikes and stuff have that reserve tank. That's basically what they're doing, is they're just pulling out of a different port so they can access that fuel. So if we take that sponge now that we just picked up and realize it's at oven dry, and we take it and we put it in the sink underwater and we squeeze it, right? You're going to have all those air bubbles coming out. You keep squeezing it, you keep squeezing, eventually no more air bubbles coming out. Now we're at that point of saturation. Okay. Now you pull that sponge up out of the sink and you're just holding it. And while you're holding it, what's happening? Right? What's happening is what we refer to as free drainage. You have more water in the sponge than the sponge can physically hold on to, with tension. And so gravity now is doing its thing. And gravity is pulling all that extra water out in the pore spaces that is not actually, adhering to the surface of a soil particle like we were talking about up here. It's just going to sit there and it's going to, it's going to drain down because of gravity. Now, after it stops, eventually, it's going to come out really fast, and then it's going to start slow to a trickle, and then it's just going to drip, and at which point it stops. At that point, somebody had mentioned this, we're at what we refer to as field capacity. Okay, and field capacity, I'm going to abbreviate as FC here. So there is a lot of water in the soil at this point, and the soil can just barely hold on to it against gravity and make it available to the plant. Okay. The problem, though, is that we do lose a lot of water between saturation and field capacity. But we need that too, because a lot of plants can't grow in that saturated condition. They need oxygen just like you and I do. All right, so now we take that sponge that's at field capacity, just barely holding on to the water. We move it over a dish that we want to wash. Let's squeeze that sponge now. We're going to wring it out, actually. We're going to wring it out all the way, get all the water we can out of it, right? And then I'm going to take that sponge and I'm going to toss it to you, and you're going to catch it. And then I'm going to ask you, is there water in the sponge? And your answer is going to be, well, yeah, there's water in the sponge, but we can't get that water out, right? And that's what a lot of you are referring to here as permanent wilting point, PWP, okay? And so this now leads us to our first little equation that we're going to learn about here, okay? And that is the difference between field capacity and permanent wilting point. Does anybody know what we call this one? I don't think I saw this one in the chat earlier. Yeah, AW, Eric, very good. Or AWC, actually the AWHC, that's how I'm going to call it. So AWHC, which is available water holding capacity, available water holding capacity. That's what the soil can hold. So going back to here, to this one over here, let's assume that we're at field capacity in this loam soil. How much water do you think is actually going to be in this, this top little piece here that we were talking about? What percentage of this is going to be water then? And what percentage is going to be air at field capacity? All right, let's see if I got any guesses out here in the chat. I got Jeff in here too, man. I got all kinds of good people. 50-50, yeah, that's true, Richard, yeah. So basically we could split this in half. And we can say that 25% of this then is going to be water. And the other 25% here is going to be air. So typically with a clay soil, you're going to be 25% water, or excuse me, a loam soil, you're going to be 25% water, 25% air, or somewhere thereabouts. Okay. So looking at this, how is all of this water, though, going to be available? Is it all going to be available? Remember, when we use our soil moisture sensors, right? We measure soil moisture content from here up. So we measure soil moisture content from here up. So if we're at fill capacity, we're actually measuring from oven dry all the way up, and that's what our soil moisture sensor tells us. So my question to you is all 25% of that water going to be available? Because remember, the sensor is measuring 25% over here, which is fill capacity. And if you're looking at the chart here, you're going to realize the AWHC only goes to here. So what percentage then might it, good answer there, no, right? So what percentage of it might actually be available, right? And just by looking at the chart, you're probably getting an idea that it's about half of it. That's right. And so that means then that about half of this is locked up, right? So I'm going to kind of, I know I'm scribbling on a vertical screen, so forgive me for not drawing very well. But about half of that's locked up. So that means only the top half of that water, or 12.5%, is available.
Wow.
Okay. So that's what's available. So now you might say, well, how do we turn that into something that we could use, right? How do we turn that into something that we could use? Well, ultimately, the way you figure out AWHC, let's go back and make this an equation real quickly. AWHC is equal to the fill capacity minus the permanent wilting point. Okay. And you might say, well, okay, if I walk up to a field, how in the world am I going to know what my fill capacity and permanent wilting point are? Maybe I know my texture, and so I can get an idea of what the texture is, but how do I actually know what fill capacity as a percentage and what permanent wilting point is as a percentage? Okay. And so often what we'll do is we can use soil moisture sensors to figure this out. You would put your sensor down below the root zone. Let's think about, why would we put it below the root zone? If you're below the root zone, ET is not going to be pulling water out of the soil, right? And so you're not going to be depleting any water. And if you're below the root zone, roots aren't using it, and gravity has probably also done its thing, meaning the soil can't hold it against gravity, so gravity is going to pull it down. So if you were to put a sensor down below the root zone, you could probably find what fill capacity is, because roots aren't pulling it up and gravity has pulled it down. So you end up at this phase where there's just amount of water that the soil can hold against gravity. And so that's how we can make an estimate of what fill capacity is. Now, we could also argue about, well, if we moved over 10 feet and we did it again, would you get a different number? And of course. So, but they should probably be all falling around the same number. In our case, our fill capacity number, remember, would be 25%. It's not what's available, it's what is there, okay? So then the question becomes, well, how do you now find permanent wilting point? Well, that one's easy. You put the sensor in the root zone and you just let the plant use water until it what? It's dead. Once it's dead, you know that's the permanent wilting point, right? Because it's that's the end, right? The plant's no longer alive. Now, with that said, though, still plenty of water below permanent wilting point. It's just the plant can't get it. And so we can use this equation right here to ultimately solve for the AWHC. And of course, what a lot of people do is they just look in a book and they say, okay, for this particular soil texture, here's the AWHC, right? So how do we turn this AWHC into a value that we can use, right? And so that's our first little equation here. What you do is you can take the 12% and you can divide it by 100, which would give us then as a decimal 0.125, right? And so that gives us a decimal value. And then you all know that there are 12 inches in a foot, right? And so knowing that, then you take the 0.125 times 12, and that gives us 1.5 inches per foot. And so that would be the available water holding capacity of a loam soil. And you could probably even think about that up here too, because remember we said the soils, let me change colors here again. The soils were 6 inches. And we said of this 3 inches was air. And then that means 3 inches is water, and we cut it in half. And so we said, well, of the 3 inches, only 1.5 of it's available. So this is the math on how you do it, but ultimately you could just think it through too, right? So what you now need to do is you need to say, okay, well then what's our root zone, right? So if we know we have this loam soil and we have a root zone of say 4 feet deep, right? And so how much water would be available in the root zone? It would just be, I guess it would be 6 inches, right? Because 1.5 times 4 would be 6. So this is then how much water would be available in the root zone. Now, do we want to use all 6 inches? The answer is no, because if you use all 6 inches, that means you're going to be depleting. By the way, that's what that's our other term here. So let me redraw this here. Soil moisture depletion is how much we drop down from fill capacity. Soil moisture content is how much is there from oven dry, right? And these two track with each other. As you deplete the water because of ET, of course, the amount of water that you have left is dropping, right? It's kind of like when you use when you use fuel in your car, right? The amount of fuel that you have left goes down. And then when you refuel your car, the amount of depletion that you have diminishes as well. And so these two are always going to be tracking together. So the question becomes, of this 6 inches that's available, how much of it do we actually want to use? If you use all 6 inches, you end up going to a depletion all the way to here, permanent wilting point, and the plant's dead, right? So we don't want to go that far, right? And so this is when we have another decision to make, and it's called MAD, as Sam just pointed out. It's called MAD, Management Allowable Depletion. And we then pick a target here, and we determine how much of this 6 inches do we want to allow ourselves to deplete? Do we want to deplete 50% of it or 10% of it, right? And it depends on your crop. If you're growing strawberries here on the coast of California, you probably don't want to stress it very much. So you might use a MAD of, say, 0.15, right? Or 15%. If you're growing forage crops, alfalfa or something, right? Out in the desert, then you might stress it more. You might use a MAD of, say, 50%. Okay, so this again is a management decision, management allowable depletion. How much are we going to allow ourselves to deplete? All right, so I'm running out of time here, and I could keep going for another hour, but one thing I do want to point out too is here's some basic available water holding capacities for the different soil textures. Okay, so if you know you're working with a clay loam, for example, right, and you'll notice there's ranges on these too. Well, why? Because we don't know it perfectly, right? And even if we did figure it out perfectly in a lab, you move over 10 feet again, it's going to be different. So you just pick a number there, right? And so a lot of times for a clay loam, somebody might be using like 1.9 or 2. And then if it's a silt loam, maybe they're using the 2.4 or something like that, right? But here you can see for our loam soil, it actually has a range of 1.5 to 2, right? And again, why? Because, well, there's a lot of soils that kind of classify in that loam range. And so we were focusing kind of on the primary loam, which is the 40% sand, 40% silt, and 20% clay. Okay, so I could keep going, but I think that's a good little start on understanding all these different pieces here. And so I guess let me give you one more equation to use, and that's the SMD max. So if you want to know how much water you can actually deplete from your field, right, this would be your equation. You would need to know the AWHC, so you need to know the soil texture in inches per foot. You need to know your root zone in feet, and then you would need to select your MAD as a percentage. And so if you were to have all of those values, right, you probably have a pretty good idea what your root zone is. You probably can make a good estimation what your AWHC is based on that table I just showed you. And then you select your MAD based on the crop you're growing. And that would tell you about how much water you could deplete between irrigation events, right? And that's really the game. And some of you have seen the soil moisture charts where they have the field capacity on the top, and they have basically the MAD down here, and then it's basically pong, or that old game, right? Keep it between those 2 points, field capacity and the MAD, and don't let it go outside of that. As it starts to get closer to the MAD over here, right? As your SMD starts to get closer to this MAD, or what we would call the SMD max, it's time to irrigate. And if you get above field capacity, well, then it's obviously time to stop irrigating. So that's some basic soil plant water relationships in a 45-minute block there for you. So
yeah, I think this was maybe a whole semester class for a while, right? So you did a great job.
Actually, we do short courses typically during the summers. They're not happening this year because of requirements from Cal Poly, but it's typically a 2-day short course for working professionals. in my university class, it's a whole week with a lab associated with it. So yeah, there's a lot to learn on this stuff. Hopefully you guys got a little bit out of this and maybe clarified some of the content or the concepts that we're using here.
Yeah, we've got a little bit of time for a couple more questions. One of the
Sure.
questions I saw was, how does percent soil moisture content translate to centibars?
Yeah, so basically centibars, so it's a little bit different. Centibars, actually, let me pull up a chart for you if you don't mind here. I think I have one. Got one right up in here somewhere, but basically they're two different things. Soil moisture content is measuring how much water's there. And I think it's got down here now, actually. Soil moisture tension is centibars. So one is about how much water is physically there. The other is about how hard the roots are pulling to get that water. And so when you look at it, this is a book that I use for my class here at Cal Poly. But when you look at it, here's kind of the relationship. And so the answer is the relationship is really dependent on the soil texture. When you have a high moisture content in clay, by the way, you can see the 25% is right around in here, right? So that's kind of like your loam soil, and this is field capacity. Field capacity would be 0.1 bars or 10 centibars. And that doesn't change. That is the tension at which it takes the roots to pull it out. Now, in order to get to that tension, though, in a sandier soil, you don't have to have as much moisture content, because the sandy soil is kind of like somebody that doesn't have a whole lot of money, right? That's willing to just give you money, right? It's like a bum that says, hey, I got a buck, here's a buck. I don't really care, it's a buck, right? Whereas the clay is kind of like a rich person that has, if you want to get $1 out of them, it's actually almost harder to get $1 from them than it is from somebody that doesn't have any money, right? And so that's kind of the relationship between clay and sand. So the answer is that the tension is the same amount, like in this case, 0.1 bars for field capacity and 15 bars for, which translates, by the way, to 10 centibars and 1,500 centibars. It's the same regardless of the soil texture. But in order to achieve that particular level of tension, you have to have so much content over here, you know, for the different soil textures. And so there's a relationship, and that's what this is called, the soil plant water relationship curve. And so so there isn't like just a number that you multiply by or something, if that's what the question was.
Yeah, so thank you. And then another thing that I often hear is I always get some confusion or hear some confusion from time to time with people when they talk about the depletion rate. And if they say 35% depletion, do they mean a drawdown of 35%, or there's 35% water in the soil?
Yeah, great
And
question.
what is the correct, how should we be talking about this?
Yeah, so typically when we talk about depletion, we want to know how much water is missing. And typically, I personally like to talk about it in inches, not actually as a percentage. So I want to know how many inches of water, like we were just doing in our example here, it can hold 6 inches of water, right? And then how many inches are we going to allow from that 6 to be depleted? So we're going to, if we had a MAD of 50%, right, you would then say, well, we're going to allow 3 inches to be depleted. And the reason why I like to work this way is because, especially here in California, I know we don't have folks, not everybody's from California, but you got a lot of weather stations here, and a lot of them monitor how much water is being used every day in inches. And so you can just say, okay, I have 6 available, and today we used a 1/4 inch, tomorrow we used a 1/4 inch, the next day you used a 1/4 inch. And so you can figure out how much you're depleting from that 6 inches. And so I typically don't like to talk about it as a percentage, because that doesn't really translate to what, you know, what we're measuring in terms of how the water is being consumed.
Yeah, and then one of my favorite water managers in Nevada, Tom Radin, he's asking,
The answer is no, 0 chance. Tom, you probably know the answer to this one, but yeah, water or roots grow where there are nutrients, water, and air. And so often people will say, well, you know, the roots are chasing water. Well, let me kind of draw this for you here. This is the soil surface. Okay. And then you got your roots, and let's just pretend the roots are like an upside down Christmas tree. Okay. Where, you know, you got most of your roots up here, and then you got a few roots down here. Well, where is a majority of your water going to be used in this root zone, right? a majority of the water is going to be used in the top half of the root zone. Why? Because that's where most of the roots are at. In fact, we have this basic rule that says in the top 25%, you'll use 40% of the water. In the next 25%, you'll use 30%, and then 20% and 10%. Okay. So that course adds up to 100% here. But in the top half of the root zone, you're using 70% of the water from the top half. And so the thought is, well, if you stress your plant, you're going to get a better root structure because those roots are going to go chasing water. Where in fact, that's not what's happening. I mean, there is some truth to what's happening, but it's not what they think. The reason why when you stress this is because you used most of the water from the top half of the root zone. These roots have basically run out of water. And it's now these roots' turn to do some work. And what are they sitting in? They're sitting in water, nutrients, and air, oxygen. And so now it's their turn to do some work. And if there was no water, nutrients, or air down here, the plant's just going to straight die. So it's not like they have a brain and they can say, I'm going to go in that direction and there's going to be water over there, right? Instead, it's just that they're in water and it's now their turn to do some work. So stressing the plant does typically create a little bit better root structure, but it's just because, those roots are required to do some work now that the top half of the root zone is not doing any work.
Yes. So then just a follow-up question to this, is there a good way to increase root zone size?
Well, you can talk about genetics, which of course people don't like to talk about sometimes. And it depends on often too, if you're in heavier clay soils, it's really hard to get the oxygen down deeper. And so you might have a tree that in a clay soil might only go 4 feet deep, but in a sandier soil might go 8 feet deep. And so there's some thought processes out there. The Maisie injectors, they've got these ideas of on subsurface drip, actually sucking air into the water and injecting oxygen in with the subsurface drip to try to promote oxygen down in the deeper roots or in the deeper layers of the zone to try to get roots down there a little bit further. So there's ideas, but really you're kind of stuck with the texture you have. You can get deeper roots in a sandier soil than you will on a clay soil.
Yeah. So Dr. Gaudi, thank you so much. You, again, very fascinating. I know we could all sit here for hours and listen more, but we're out of time. But I did want to say thank you. And especially, I know you're coming to the end of your quarter and you've had a tough time. So thank you. Appreciate your time. Thanks everybody for listening in. We really appreciate that. We'll hope you'll come back on Friday when we're going to be talking about the best ways or how to figure out the best ways to irrigate your tree crops. So again, Dr. Gaudi, thank you. And thanks everybody for joining.
Thank you guys.